Okay, so in section 1.2, we are talking about limits of functions. And here's some of your homework questions that I've got for you here. Number one, what we're doing is we're looking at a graph and we're deciding whether limits exist, okay? And so this is a good one to consider. So the limit of the function, of course, the function is in red. We've got a gap here. We've got an asymptote there. It looks like it's continuous everywhere else that we can see, okay? So the limit of the function as x approaches 3. So as x gets really close to 3, which is right here, as x gets so close to 3, it appears that the function gets really close to, looks like 1. Now that's just a little less than 1. I think that's supposed to be exactly 1. So I think your answer here is going to be 1. Again, x approaches 3. From both sides, you can see that the function approaches 1 here, okay? What about the function as x approaches 2? Well, here's 2, and definitely the graph is coming towards y equals 0. And as a matter of fact, f of 2 equals 0. So that confirms it. There's 0. Okay, the limit of the function as x approaches -1. Well, -1 is here, and even though at -1 the function is not defined right here, it's a gap, we can still consider the limit. And the limit definitely appears to be approaching, as it gets infinitely close here, to y equals 1. So even though the function is not defined at that point, there is a limit. The limit of the function as x approaches 4. Well, as x approaches 4, we have a vertical asymptote. And so the function races towards positive infinity on the one side, and it races towards negative infinity on the other. This graph is definitely not meeting at a predictable y value point. So because they're going in opposite directions, there is no limit. So you can say the limit does not exist. And we're going to be writing this quite a bit in calculus. So you can write D and E. I'll know what that means. Does not exist. Okay. All right. So that's question number 1. Like I say, just let me know if you have any questions about question number 1 there. I will be moving on to question number 2 here now. So question number 2 in your assignment looks like this. It says state the value of each limit. And again, if we have a polynomial function, simply substitute the value in because it's continuous, and then you'll get the limit. If it's a constant function or an irrational function or something like that, we may have to do some further thinking, but this should be pretty easy. These are all kind of monomials, right? So A, what's the limit of x cubed as x approaches 2? Well, because it's a polynomial continuous function, I simply substitute 2 in for x, and that equals 2 cubed, or 8. Real easy. What about a constant function? Remember, y equals 3, or the function f of x equals 3 is just a horizontal line going through y equals 3. And so it doesn't matter what x does. This is always going to be 3. So if it's a constant function, the limit is 3, because it's 3 all the time. All right, what if x approaches k? Again, polynomial function, substitute this value in for x, and we get k to the 6. That's your limit. That's your limit. Doesn't have to be a number. Okay, if the limit of the function x as x approaches pi, well, you substitute. So the limit is pi. What about the limit as of the function root x approaches 4? Easy, plug 4 in. It does yield us a real value. That's 2. Done. This is a constant function, horizontal line of 3.14 all the way across. So as x approaches 0, the function approaches just pi. It stays pi all the time. So that's easy. That's question number 2. Monomials, just substitute. It gets a little bit tricky in question like number 4. So I'll do A and B here. And then I might do a couple more in a few minutes. But the first thing you want to try, because again, these rational functions are continuous on a lot of the domain. There's lots of continuous parts. So just plug your number in and see if you get a real number. Chances are that's the exact limit at that point. But here we see if I plug a -2 in my denominator, that causes a problem. -2 squared is +4, minus 4 is 0. So I can't just simply substitute. What I have to try and do is I have to try to factor and divide out any common factors. Then I can maybe simplify this into something where I can find out what this limit would be. And so I'm going to do this. And I do want you to rewrite this limit notation every time, every step. I know. Every step though. So you don't forget what you're doing, and so I can see that, because really the limit is not equal to the expression. So show me what you really mean. So this is x plus 2, and I'm going to factor this x plus 2 times x minus 2, right? Because that's a difference of squares. And what I can do now is I can divide out my common factors, and the limit, and you can get really messy with your limit like I do. You know, it doesn't have to be neat. You have to write it so many times. It's okay. So this is now reduces to 1 over x minus 2. Now, can I substitute here? Yeah, I totally can. That doesn't give me 0 anymore. So look at this function, okay, if this was a function, behaves exactly like this function, except for the gap, right? And so I'm going to plug in x equals -2. And now you can drop the limit notation, all right? And you can just put 1 over -2 minus 2. So when you substitute to try and find the limit, then you drop the limit notation. I've had lots of students write this limit notation all the way through, even to the answer. No. You're looking for the value. This is how you're finding the value. Once you start to substitute, you're just looking for the value. What you can do is this, though. This is 1 over -4, right? So you can say the limit of x plus 2 over x squared minus 4 as x approaches -2 equals 1 over -4. You can write that. Or you can just circle this and I'll know that that's your limit, okay? So one or the other. What about b? Let's do b here real quick as well. So b, again, if I plug in 1 in here, I get a fine value up here, but I get a 0 down here. That's a problem. Let's see if I factor this, if I can simplify this expression. So I'm going to factor this trinomial and numbers that multiply to +2 and add to -3. So that's going to be x minus 2, x minus 1. X minus 1 on the bottom. I can now divide out common factors. And as x approaches 1, this function now behaves like x minus 2. Now, in order to find the limit, I can substitute. So I'm going to substitute 1 minus 2, -1. And that is the limit of the function. Don't believe me? Let's graph it on Desmos. So remember, this function is going to look like the function x minus 2. And I graphed it on Desmos over here. Here it is, x squared minus 3x plus 2 over x minus 1. It certainly does look like the line x minus 2. Okay, it's a y equals x, but it's moved down 2 units. So if I want to know what the limit as x approaches 1 is, I simply plug 1 in. It should be -1. So let's just see. 1, -1. Look at that. Okay. Now, on the real graph, it's undefined. But if you substitute what this graph looks like with the actual line of x minus 2, then you can substitute and you'd find out what that limit actually is. Okay. It's undefined there, but the limit is clearly -1. Okay. Okay, you're probably interested in something a little bit more difficult. I did do G on a different video, so you can watch a different video. I'll show you how I did G. The hint here for G is what you want to do is either rationalize the denominator or factor the top and the bottom. How do you factor the top and the bottom, you say? Treat this as a difference of squares, and then you'll be able to simplify. So that's the hint for G. But because I haven't done E or F, I'll probably just do one of them just for the sake of time for this video. But notice here, guys, notice this is a difference of cubes. This is a difference of squares. So you have 2 different ways that you can factor those out, right? So the limit as x approaches 1 here, a difference of cubes. I am going to take the cube root, and I'm going to keep the same sign. Take the cube root of 1 is 1. All right. I am going to then write a squared, so that's x squared. This is opposite sign. 1 times x is just x, and this is positive always, 1 squared. And over here I can factor that as x minus 1 times x plus 1. All right? That's going to be great for us because we can divide out this factor with this one, common factors. And what I'm left with now is just this right here, aren't I? And I can plug in 1 there, no problem, because I don't get a 0 anymore. So what this is saying is that This graph mimics this one identically, except for that one little hole. And so if I plug 1 in, I can find out what the limit is on the original. So we'll do that, and I'll plug that in now. So 1 squared plus 1 plus 1 over 1 plus 1. That's 3 over 2, looks like. So that should be your limit as x approaches 1 for this graph. Don't believe me? You can graph it and take a look at the graph. Okay. Same thing over here. I won't take the time to do this one, but this is a sum of cubes, and you can factor the sum of cubes. You're going to be able to factor that out with another factor down here. Substitute -3 in. Boom. Bada bing, bada boom. Get a value. And you're done. All right. So that's some homework questions. Your homework questions for 1.2 Calculus 30.